Now let's introduce a new concept. The difference between conservative force and non-conservative force. A force is conservative if the work it does on an object moving between 2 points is independent of the path taken. Gravity is a classic example. The work done by gravity on the person moving from the platform to the water is the same as if the person dives straight down or go down the winding slide. It only depends on the starting and ending heights. A non-conservative force, like friction, is opposite. The work done by friction does depend on the path. Pushing the book along the long rust-colored path involves more work against friction than the shorter blue path. Friction is also called a dissipative force because it removes mechanical energy from the system, which we will discuss later. So, key point to take: conservative force, the work done by the force is path independent. Now here are key property, and they are all equivalent to each other. For conservative force, the work is path independent. It's reversible. And the work done over any closed path is for conservative force is zero. Most importantly, for conservative force, we can associate a potential energy to it. We can rewrite the work energy theorem in terms of the work done by conservative force and non-conservative force. Because the network is just the sum of work done by conservative force and work done by non-conservative force. Think about it. A force is either a conservative force or a non-conservative force. There is no force doesn't belong to either of them. Since gravity is a conservative force, we can define a potential energy associated with it: gravitational potential energy. Potential energy is essentially stored energy that an object has due to its position or configuration. When an object falls from a height from yi to yf, the work done by gravitational force is positive and equals to mgyi minus mgyf. We define the change in potential energy. Let's call it change in potential energy as a negative of the work done by the conservative force, which in this case is gravity. This means at the book force, gravity does positive work, and the book's potential energy decreases. Because we define change in potential energy as negative of the work done by conservative force. Conservative force doing positive work at the book force. So change in potential energy is negative in this case. And it's also intuitive. The book force is potential energy decreases. And by that, we can simply write gravitational potential energy as mg. Y is the position of object. So we have the formula for gravitational potential energy. Potential energy, gravitational potential energy, it's mgh. Its unit is 1 Newton times meter equals 1 joule. It's the energy an object has because of its height h related to some chosen zero level. A key point here is that you can choose your zero level to be anywhere you want, the ground, the tabletop. What matters physically is the change in potential energy. So what really matters is the change in height. Let's check our understanding. We have a 15 kilogram drone moves from a height of 7 meters to 13 meters. What's the change in its gravitational potential energy? So mghi, that's the initial potential energy, mghf. So the change and putting in what the numbers, g is 9.8, right? Changing height is 6 meters. So roughly, so the answer is E. Finally, using the relation shown, we can write an extension of the work energy theory. The equation says the work done by non-conservative force is equal to the change in the kinetic energy plus the change in gravitational potential energy. Work done by non-conservative force equals change in kinetic energy plus change in potential energy. Now, what's going to happen if non-conservative force doesn't do any work? If the work done by non-conservative force is just 0, then the change in kinetic energy and the change in potential energy always add up to 0, right? And we can rearrange the equation. We can find the sum of kinetic energy and the sum of potential energy is always the same, is a constant. So this gives us mechanical energy conservation or conservation of mechanical energy. The statement is as follows. The total mechanical energy, which is the sum of kinetic energy and potential energy, of an object remains constant if the net work done by external non-conservative force is 0. If the work done by non-conservative force is 0, then mechanical energy is constant. This is conservation of mechanical energy. And always remember what's the condition for it. The work done by non-conservative force is 0. Now we want to explain a little bit more in depth that the reference level for gravitational potential energy. The choice of 0 level for potential energy is really whatever you want to choose it to be. What's important that you have to make it consistent, because what matters is the difference in potential energy between 2 points. And as long as you choose the same point as a reference point, the difference will always be the same, no matter which point you choose as your 0. Now, let's look at this very classic conceptual problem. We have 3 identical balls thrown from a building with same initial speed, but in different directions. Ignoring air resistance, ranking their speed when they hit the ground, which ball of those three, 1, 2, 3, will have highest speed when they strike the ground. We can try to understand this using conservation of energy. The initial energy of the three balls are all the same because they have the same speed, thus the same kinetic energy, same height, same potential energy. The final energy is 1/2 mv squared. And energy is mechanical energy in this problem. Is it conserved? So you have to think whether there is any non-conservative force doing work to the ball. Because all three balls have the same mass starting from the same height and have the same initial speed, they all start with exactly the same total mechanical energy. And we ignore air resistance, so there's no non-conservative force doing work to these balls. So they should have the same final mechanical energy. And their final position are the same. Their final position are the same, which means their final potential energy are the same. Which means the final kinetic energy has to be the same. If their final kinetic energy are the same, they must have the same speed. So the answer is 4.